Tonight's presentation is titled Piston Engine Inefficiency, and our presenter is Mike Bush. Mike is President, CEO of Savvy Aircraft Maintenance Management. He is an A&P certificate with IA authorization holder. He also has a certified flight instructor's certificate. He's an author for numerous aviation publications. In 2008, he was recognized by the FAA as the Aviation Maintenance Technician of the Year. Mike's a member of EAA. We're lucky to have him with us to talk to us and volunteer his time to share information tonight about piston engine inefficiency. Mike, thanks for being with us. I'm going to turn control of the presentation over to you.
Well, good evening, Tim. Good evening, everybody. Looks like we have a tremendous turnout tonight. Almost 560 people in the room. I am in a strange place right now. I'm in the basement of a hotel in Burlington, Massachusetts. I'm out here attending a two-day meeting, actually the first Piston Engine Summit meeting held by or hosted by the FAA's Engine and Propeller Directorate that's located in Burlington, Massachusetts, just north of Boston. And so I spent all day with a whole bunch of folks, including several EAA people and people from other alphabet groups and Lycoming and Continental and all sorts of people and lots of FAA people, and we're going to do it again starting at 8:30 tomorrow morning. So at any rate, I'm in the basement of the hotel, which was the only place I could find that both had an adequately good internet signal and a sufficiently low noise level that I could do this. So I hope it goes smoothly. As Tim said, tonight we're going to be. This one's a little bit of a change of pace from the kind of stuff I usually do. The title is Engine Inefficiency, and my slide's not changing. There we go. And I'm going to be talking about why our piston aircraft engines are as inefficient as they are, and how what we can do to improve that. Our piston aircraft engines are machines that convert chemical energy from fuel, from aviation gasoline, into useful mechanical work that turns propellers and hopefully generates airspeed. But in fact, they don't do that job very efficiently. In fact, if you do everything as right as you can with a typical piston aircraft engine of today's technology, and you set up the power settings just right, you lean just right, you do everything just right, about the best you will wind up doing is converting 34% of the energy in that avgas into useful work that turns the propeller and propels you through the air. And fully 66% of that energy in the fuel is wasted. A lot of it goes out the exhaust pipe, a bunch of it goes out other places. We'll talk about how it's wasted exactly. But you know, in a world of $4 or $5 avgas, it's a little bit depressing to think about the fact that 2/3 of the energy in that fuel that we buy is basically being thrown away and not doing anything useful. So we're going to be talking about why that is, and then a little bit about what we can do to improve the efficiency. Now, when I first saw this figure, that this 34% was pretty much the best we could expect in terms of efficiency out of a piston aircraft engine, I was kind of surprised, and it seemed hard to believe that our piston engine technology was really that inefficient. But a little arithmetic will convince you of that. So I'm just going to go through a little exercise, do a little math. I promise you that there won't be any Greek letters and that there won't be a quiz at the end. But let's just go through this with me and have a little bit of fun. Imagine, consider a beach bonanza with a Continental IO 550 engine. It's rated at 300 horsepower for takeoff. This is a normally aspirated engine at 26.6 gallons per hour of fuel flow at full takeoff power. And that's the 26.6 gallons per hour is the red line on the fuel flow gauge. That's what the factory says it's supposed to burn when it's putting out 300 horsepower. So let's figure out how much fuel energy it takes to produce that 300 horsepower. So follow me through on this. We start with 26.6 gallons an hour and multiply it by 5.85 pounds per gallon, which is what avgas weighs at standard temperature. And we come out with a fuel flow of 156 pounds per hour. Now, if we convert that pounds per hour into pounds per second by dividing by 3,600, we get 0.0433 pounds per second. So the engine is using 0.0433 pounds of fuel per second. Now, 100 low lead fuel contains 18,700 British thermal units of energy per pound of fuel. So if we're burning 0.0433 pounds per second, we multiply it by 18,700 BTUs per pound, we find that the engine is consuming 810 BTUs worth of energy per second. Now, 1 BTU per second is equivalent to 1.4 horsepower roughly. So 810 BTUs per second is the equivalent of 1,145 horsepower. So that says that this engine, when it's producing full takeoff power, is consuming 1,145 horsepower worth of energy from the gasoline in order to produce 300 horsepower at the propeller. And if you divide 300 by 1145, you'll discover that that's an efficiency of 26%. That's even worse than the 34% number I gave you earlier. I'll tell you why that is. But that's pretty depressing. So basically, we're only making use of about a quarter of the energy in that gasoline when we're running the engine at full takeoff power. And we're going to go into exactly why that is. But before I do, let's also examine that 26.6 gallons per hour. Why does an IO 550 producing 300 horsepower really need to consume that much fuel? And again, we can do a little arithmetic. The engine is rated at 2,700 RPM for takeoff. That's the RPM red line on the tachometer. Now, since these are four-cycle engines, four-stroke engines, and each cylinder produces a power event once every other crankshaft revolution, you know, suck, squeeze, bang, and blow. It takes 4 strokes or 2 revolutions for a full power cycle. So there are 1,350 power cycles per minute. In other words, 1,350 times per minute, all 6 cylinders do a power cycle. Now, the engine is rated at 550 cubic inch displacement, and it's about 1,700 cubic inches in a cubic foot. So 550 cubic inches is 0.32 cubic feet, about a third of a cubic foot. Now, so in theory, the engine should be breathing 0.32 cubic feet of air every time it does one of these power cycles, 1,350 times a minute. Now, in fact, the engine can't breathe that much air simply because there are losses in the induction system. We lose, there are losses going through the induction air filter, going through the induction plumbing, going through the throttle body, and trying to squeeze its way through the intake valves. And so these engines actually only are able to breathe at full red line RPM, are only able to breathe about 85% of what their theoretical displacement is. That's what's called volumetric efficiency. And volumetric efficiency goes down as the RPM goes up, and we're trying to squeeze the air into those cylinders faster and faster and faster. So at 2,700 RPM, we can only squeeze about 85% of that 550 cubic inches, or 0.32 cubic feet, into the cylinders every power cycle. So instead of breathing 0.32 cubic feet of air per power cycle, we're only able to squeeze in about 0.27 cubic feet. Air at sea level weighs 0.0765 pounds per cubic foot. So if we multiply that out, the amount of air that we can cram into this engine every minute weighs 27.9 pounds. Best power mixture, if we were running the engine at best power mixture, that is 12.5 to 1 air-fuel ratio by weight. So if we're cramming 27.9 pounds of air per minute into the engine, to maintain 12.5 to 1 mixture, we have to cram 2.23 pounds of fuel per minute into the engine. And if we convert that in pounds per minute to pounds per hour, we get 134 pounds per hour, or we convert it to gallons per hour, we get 22.3 gallons an hour. Now the POH calls for 26.6, not 22.3, and the reason is that that we can't run the engine at best power mixture at full rated power because there's not enough detonation margin. And so for full takeoff power, we run an unusually rich mixture. So instead of 12.5 to 1 by weight, the mixture is closer to 10 to 1 by weight when we're running at full takeoff power. And so the fuel consumption is 26.6 gallons an hour. But I'm just going through this not so that you can reproduce the calculations, but that you can sort of see that there's some logic in how this all computes out. Now, how about when we try to operate the engine in cruise and run it as efficiently as we can? We're going to lean it way back to a nice lean of peak setting at 65% power and try to get stuff nice and efficient. At 65% power, a 300 horsepower engine produces 65% of 300 horsepower, or 195 horsepower, and it burns about 13 gallons an hour. And again, we can go through this same calculation, and I won't go through all this with you, but 13 gallons an hour of avgas is the equivalent of 573 horsepower worth of energy. So to produce that 195 horsepower, we use 573 horsepower worth of avgas energy, and so that now the engine is running at 34% efficiency, which is the number I gave you on that first pie chart. So even when we do everything about as right as we can, and we lean very carefully and very aggressively, and we run at a nice low power setting, we're still only 34% efficient. So let's talk about why these engines are as inefficient as they are. And there are a number of ways of looking at that. One is to look at the various ways in which the engine has losses from what a theoretically perfectly efficient engine would have. And a really nice breakdown along this line comes from a book called Performance of Light Aircraft by John T. Lowry, PhD, pretty well-known book among EAA members, I think. And he breaks it down this way. The biggest single inefficiency issue are what are called auto cycle losses. And what that means is our four-stroke engines are what are technically known as auto cycle engines. Auto cycle is the four-stroke process. It was invented by a German guy named Otto. And for an auto cycle engine to be 100% efficient, it would have to have an infinitely high compression ratio. In other words, it would breathe in as much air as it could, and then it would compress it down to nothing before the spark ignited it. Now, of course, a real engine can't compress it down to nothing. In fact, if it compresses it too much, we wind up having detonation. And so in order to provide adequate detonation margins, most certificated avgas aircraft engines are built with an 8.5 to 1 compression ratio. Some of the older engines that were certified to run on lower octane fuel, on the old 80 octane fuel, those were limited to 7 to 1 compression ratio. But more modern engines that are certificated for 100 octane fuel, the compression ratio has been raised to 8.5 to 1. And you really can't go above 8.5 to 1 without starting to cut into a detonation margin. In fact, I know that there are quite a lot of tricked out Lycoming engines flying around in the experimental community that were built with pistons that bring the compression ratio up to 10.5 or up to 10 to 1, and produce more power that way by reducing auto cycle losses. But in my view, it's really not a safe thing to do, because what you're doing to get that extra horsepower is you're eating into your detonation margin. And the likelihood of having a catastrophic detonation event on takeoff is much greater if you build an engine with 10.5 to 1 pistons than if you limit it to 8.5 to 1, which is as high as the FAA will certify an engine. I think the highest compression ratio I know of on a 100 octane certified engine is 8.6 to 1. Any higher than that, and the engine simply won't meet the detonation tests that are required for it to be certified. So if you're operating at a higher compression ratio than that, you're test pilot. And but at an 8.5 to 1 compression ratio, an auto cycle engine is only at best 57.5% efficient, because we're not compressing the fuel any more than 8.5 to 1 before we ignite it. As we mentioned, there's also the problem of volumetric losses. That is, the fact that the induction system is not perfectly efficient, and that there are losses trying to get the air into the cylinders that typically run about 15% loss from the theoretical displacement of the engine. So volumetric efficiency is about 85% on these engines. Mixture losses, that's the fact that we tend to use mixtures that are richer than the best economy mixture. And the reason we do is that when we run best economy mixture, which is a very, very, very lean mixture, the engine doesn't put out as much power as it would at a richer mixture, and so we don't go as fast as we'd like to. So optimum mixtures are typically used by cafe racers and stuff, but when you're flying cross countries, or particularly if you're flying exhibition, we tend to use much richer mixtures than the optimum mixture. And so mixture losses, even when we're running at a reasonably efficient lean of peak cruise power setting, is about 10% or so. Then there are mechanical losses. Mechanical losses are largely due to friction. And the frictional losses of engines vary with RPM. The friction loss varies basically with the square of RPM. So the higher the RPM, the more friction loss we have, and it goes up pretty rapidly as RPM increases. But typical mechanical losses are on the order of 12% that we're losing to friction. And there's friction in various places in the engine, but the biggest frictional losses are the friction of basically the ring pack running up and down inside the cylinder barrel. Then there are accessory losses. Those are due to the fact that we don't just turn the propeller with this engine, but we also turn some other things that don't contribute to airspeed. We turn magnetos, we turn alternators, sometimes we turn vacuum pumps and hydraulic pumps and stuff. So we lose maybe another 5% to driving these accessories, particularly magnetos. And then there's just sort of a grab bag of other losses, things like blow by past the compression rings because the rings don't seal perfectly, and some other minor losses. And so if we take all of these things and we add them up, or more properly, we multiply them out, we wind up with a result of 34%, which is the number that I started this discussion at. So this is one way of looking at the efficiency issue. A completely different way of looking at the efficiency issue is one that I got from a textbook called Fundamentals of Power Plants by Joseph Liston. And this is basically saying, where is this energy going? Part of it's going to the propeller. The rest of it must be going somewhere else. The energy is never created or destroyed. So if we're only using 34% of the energy and the fuel for useful work, then the rest of it must be going somewhere, and this is an analysis of where it's going. And basically, a little more than half the energy in the fuel winds up going out the exhaust pipe. Now, this number is based on a normally aspirated engine. In turbocharged engines, we try to recapture some of that energy that would otherwise go out the exhaust pipe by sticking a turbocharger in there and having some of that energy drive an air compressor. On the other hand, turbocharged engines tend to have a lower compression ratio than normally aspirated engines. So what we gain recapturing exhaust energy, we wind up losing in auto cycle losses. So there's no free lunch in aviation. But a little over half the energy goes out the tailpipe in the form of hot air, basically. It's not just hot air, it's hot air with a lot of carbon dioxide and a lot of water in it, and some smelly stuff. 12.2% of the avgas energy is used to generate unuseful heat other than the exhaust. For example, we heat up the cylinders, and we heat up the cylinders so much we have to run a bunch of cooling air over them so that they don't melt. Now, a perfectly efficient engine with an infinitely high compression ratio, the cylinders would run cold because 100% of the energy would be getting turned into crankshaft rotation, And none of it would be used to heat up the cylinders. But of course our engines aren't perfectly efficient, so we're losing a bunch of energy warming up cylinders, which we didn't particularly want to do. It's just part of how these things work. We also waste some energy warming up oil. Again, a perfectly efficient engine, the oil would run at ambient temperature. It wouldn't run hot, because we really want as much energy from that fuel as possible to be turning the prop, rather than heating up the oil and heating up the cylinder fins and so on. So we lose 51.6 plus 12.2 to heating stuff up: exhaust gas, cylinder fins, oil, etc. Then we lose another 4.3% to friction, and what's left, according to Liston's calculations, is about 32%, which is pretty close to the 34% we got doing the calculation the other way. So, so this is another way of looking at it. And in fact, this Liston way, although it's not as interesting in terms of where the inefficiencies lie, it corresponds more to the kinds of stuff we can see in the cockpit, because we've got a bunch of gauges in the cockpit that, if you think about it, measure wasted energy. We've got an exhaust gas temperature gauge that measures how much energy we're throwing out the exhaust pipe. That's what it measures. We've got an oil temperature gauge that measures how much energy we're wasting by heating up the oil, and a cylinder head temperature gauge that measures how much energy we're wasting by heating up the cylinders. None of those things are things we particularly want to do. We'd love to have the oil run at ambient temperature and the cylinder head temperatures run at the ambient temperature and the exhaust gas be at ambient temperature and all of the energy being used to turn the propeller. But that's not the way it works, and these gauges are indications in the cockpit of all of this energy that we're throwing away, heating up exhaust, heating up oil, heating up cylinder heads. And then we've got yet another gauge in the cockpit that shows the energy that's actually doing some good, and that's our airspeed indicator. And that's what we really want the avgas to be doing, is rotating that airspeed indicator instead of deflecting these other three instruments. Okay, so let's talk a little bit about how we could improve the efficiency. Now, as we saw, by far, the biggest component of inefficiency is auto cycle losses. And for auto cycle losses to be reduced, we have to increase the compression ratio. But as I mentioned, in order to increase the compression ratio without eating into our detonation margin that we need for safety, we have to use higher octane avgas. We used to have higher octane avgas. We used to have 100, 130. You remember the purple gas? And we don't have that stuff anymore. In fact, the trend is the opposite direction. The EPA is breathing down our necks to get rid of 100 octane fuel and go to an unleaded fuel that would be rated at 82 octane, which in terms of auto cycle efficiency is a big step in the wrong direction, because we can't run 82 unleaded through an 8.5 to 1 compression ratio engine. So the secular trend is against us being able to do better with auto cycle efficiency, simply because they're taking our octane away. The best solution is to eliminate the need for detonation margin by switching to diesel engines. A diesel engine is basically an engine that runs in detonation all the time. Because we're not worried about detonation margins, because we want the fuel to detonate. That's what diesel engines do with it. Diesel engines can have much higher compression ratios than spark ignition engines. And you know, the typical diesel aircraft engines that we're starting to see at AirVenture every year. I know guys from Delta Hawk are here at the Engine Summit. have compression ratios up around 18 to 1. And so their auto cycle efficiency is much, much, much better than any spark ignition engine. And in fact, one of the things that's really pretty eye-opening is if you ever run a diesel engine and look at what the EGTs are. The EGTs on diesel engines are just amazingly cool because so much less energy is going out the exhaust pipe, and so much more is turning the crankshaft and turning the propeller. So personally, I believe that diesel engines, and there are problems with diesels. There's problems getting them light enough. There's problems with the severe power pulses that for example, we can't seem to run metal props on diesel engines because the power pulses are so sharp that it fatigues the props, and so we have to use composite props on diesels. And so there's some problems, and getting them started is more difficult, but we're well on our way to solving the problems, and I think that diesel engines represent the best hope for the future of piston GA. They're just inherently much, much more efficient engines. For spark ignition engines, and we're going to be with spark ignition engines for quite a while now, probably the best thing we can do to reduce auto cycle losses is to switch to electronic ignition systems that have variable timing and that have detonation sensors, so that we can run higher compression ratios. We can run those 10.5 to 1 pistons that I was railing against because we have a smart ignition system that detects the onset of detonation and retards the timing to stop it in its tracks. And once we have smart variable timing ignition systems, we don't have to have all that detonation margin that we presently have to have for safety. And so we can increase the compression ratio. Now, we're not going to be able to increase it 18 to 1, but maybe we can increase it to 10 to 1 and get lower auto cycle losses. So the diesel engine is probably the best solution to the auto cycle loss problem. For spark ignition engines, variable timing electronic ignition with detonation sensors will help improve that. Volumetric efficiencies, there are a lot of little things we can do to improve volumetric efficiency a little bit. We can go to tuned induction systems. We can go to larger intake valves or multiple intake valves. There are a fair number of car engines now that have 2 intake valves per cylinder. We don't have any aircraft engines like that, at least flat engines, just because I guess the weight penalty and the complexity penalty, it's not been considered worthwhile. There are some little things we can do to the contour of valve seats to make them more efficient. Ram recovery, air scoops, turbocharging. Actually, another thing just occurred to me, that we get better volumetric efficiency if we can turn the engine slower. So there are a number of things that we can do to get small improvements to volumetric efficiency. Mixture losses, we've already made vast improvements in that area because there's been a campaign over the last 20 years to educate pilots to lean much more aggressively than they used to, and a lot of people are running lean at peak now. 15 years ago, anybody who ran lean at peak was considered to be a lunatic. Now we know it's the best way to run the engines. We've now got position-tuned fuel injection nozzles that improve mixture distribution and allow us to run the engines much more aggressively lean without them running rough. We've got improved engine instrumentation that again allows us to run these engines much leaner than we used to. So in terms of the mixture losses, I think the big improvements have mostly been already made. Maybe some improvements with FADEX are going to be possible, but not much. Mechanical losses, we can again, make some small improvements by using low RPM, high manifold pressure cruise configurations with controllable pitch props, or if it's a fixed pitch prop, installing a cruise prop rather than a climb prop to turn the engine slower. Because again, remember, frictional losses vary with the square of RPM, so reducing the RPM a little bit pays off pretty big dividends in reducing frictional losses. And again, there's been a big pilot education thing here. When I learned to fly a controllable pitch aircraft back around 1960 something or other, I was always taught that that low RPM, high manifold pressure would blow up the engines, and it was taught you never you never operate them under square or over square and all that kind of stuff that we now know is nonsense. But to minimize frictional losses, we always want to operate the engine at the lowest RPM and highest manifold pressure that the manufacturer allows. The use of all synthetic oil will help just a little bit because it's got better lubricity. We can't use all synthetic oil now because we're running leaded fuel, and synthetic oil and leaded fuel don't get along very well. You remember Mobil brought out an all synthetic oil called Mobil AV1 that wrecked a whole lot of engines because of the lead sludge buildup, and so we don't have any all synthetic oils for piston aircraft engines, at least certificated ones. But once we start running unleaded fuel, which we will sometime in the next 10 years or so, then going back to all synthetic oils is worth another look, because the only problem with synthetic oil is that it doesn't get along with lead in the fuel. But other than that, it's really great stuff. So when we get rid of leaded avgas, then we can start using all synthetic oil again, and that'll help reduce frictional losses because synthetic oil is a lot slipperier than dead dinosaurs. Accessory losses, basically the way you cure accessory losses is to get rid of the big power robbing accessories, and we're making progress. We're starting to see electronic ignition systems that eliminate the need for the big tractor mags. We're starting to see all-electric airplanes that eliminate the need for other accessories like vacuum pumps and hydraulic pumps. They do require alternators, but they get rid of some of the other accessories. So between getting rid of magnetos and getting rid of vacuum pumps and hydraulic pumps, we can improve the accessory loss situation. So with real good attention to detail in all of these areas, and with a spark ignition engine, we probably can hope to get efficiency up to roughly 40% instead of 34%. But to do better than that, we're going to have to convert over to diesel engines. And my feeling is that's where the future of piston GA is, both because the diesel engines are so much more efficient, and simply because it's a Jet A world out there, and avgas is going to go away someday. It's not going to go away real soon, but it's just not real cost efficient. Nobody's too excited about producing aviation gasoline. I think diesels are the future and probably the best answer that we have. So Tim, that's all I have prepared tonight. We can open it up for some Q&A. I don't know if I have a lot of answers, but we can at least have some fun discussing stuff.
Right on. There's a lot of theory here, isn't there?
Yeah. Like I said, this is a little bit of a change of pace.
So Carlisle's just wondering, what about GA turbine engines which use diesel?
Well, turbine engines are dramatically less efficient than piston engines, the turbine engines have a lot of advantages, but efficiency is not one of them. in fact, one of the ways you can that shows up a lot is when there are a bunch of STCs for taking airplanes that were designed for piston power and converting them to turbine power. You know, there's turbine-powered Bonanzas and there's turbine-powered Cessna 210s and stuff. And when you try to convert a piston aircraft to turbine power, the biggest problem is, where are you going to put all the extra fuel that you need to run that fuel-hungry turbine engine? Because turbines are, like I say, they're wonderful in many respects. You go very, very fast. They're extremely reliable. They don't have a lot of parts flying around. Their parts count is very low. But the big thing about turbine engines is they're very, very, very fuel inefficient. If we're trying to improve fuel efficiency, turbine engine is exactly a step in the wrong direction. Diesel engine is a step in the right direction.
And following up on that, Carl's wondering, what was that theoretical efficiency of a diesel engine?
Oh, I don't happen to know the number offhand, but it's probably up in the 60 area.
And since you brought up the diesel, a number of questions about diesel. David was just kind of wondering, how does diesel emissions compare to 100 low lead emissions, given all the attention to the climate change issue?
Well, again, I'm not an expert on that. I know that for several decades I used to drive a diesel-powered Mercedes 300 SD, which had totally filthy exhaust. Nowadays, we have diesels that are extremely clean, and there's a bunch of different technologies that involve, but a big part of it is that the fuel that we're using is much lower in sulfur and so on. But I'm not an expert on emissions, and so I can't really comment on that. But I've never heard anybody complain about the diesel emissions. I mean, the big flap over emissions with piston GA is simply the fact that lead is very toxic, and the environmental guys want to see it go away. And we don't use lead in diesel fuel.
And Philip's wondering about detonation sensors, and how would those work to improve efficiency?
Well, it's a question how they work or how they would improve efficiency. I'll tackle both of those. Detonation sensors, there are a couple of different ways to do it, but the most common way is, for all intents and purposes, to strap a microphone onto the cylinder, and so that if the cylinder starts to detonate, the sensor can basically hear the knock, and then alert a computer that is controlling the ignition to retard the ignition timing enough to make the detonation quit. And this would all happen, in milliseconds, basically, so that for all intents and purposes, the detonation would just be stopped dead in its tracks. Because we use fixed-timed magnetos that aren't smart, and because pilots can't sense detonation from the cockpit very easily, so we can't let our foot off the gas when we hear the knocking start as the car is going up the hill. What we have to do is provide so much detonation margin that we just know that the engine is not going to go into damaging detonation even under worst case conditions. That's very wasteful, but that's the way we do it today. The smarter way to do it is to not have all that detonation margin so that we can increase the compression ratio, but have a technology that can sense the onset of detonation and then stop it by changing the ignition timing. And that's the direction I think things are headed as far as spark ignition engines are concerned.
John's wondering how much boost to horsepower can be achieved in a normally aspirated engine by adding a tuned exhaust.
I can't give you a good number for that. I do know that we've done some tests on the power flow system, which is an STC exhaust system for Lycomings and various things like Cessna 172s and so on. We know we're able to get, another 10, 15 horsepower out of the engine just by putting a tuned exhaust system on it. I can't give you exact numbers, but it's significant.
And Walt asks, do turbocharged engines have a relatively lower exhaust temperature, i.e. some heat energy recovered to the spinning the turbine?
Well, it depends on where you're measuring it. We normally measure the exhaust temperature of a turbocharged engine with a TIT gauge, a turbine inlet temperature gauge, which has its probe located at the inlet of the turbine. In other words, it's what the temperature of the exhaust is as it's going into the turbocharger, not as it's coming out. I don't think I've ever run into an engine where the post turbocharger exhaust temperature is instrumented. And the TITs, the turbine inlet temperatures of which is basically the same as the exhaust gas temperature in a normally aspirated engine. TITs in turbocharged engines are a lot higher than the EGTs in normally aspirated engines, simply because the turbocharged engines have lower compression ratio and therefore have lower Otto cycle efficiencies, and so less heat is extracted and more heat goes out the exhaust. So the TITs tend to be higher. The other engines that have very high exhaust gas temperatures, as I mentioned, are some of the old normally aspirated engines that were originally certified for 80 octane gas, and have only 7 to 1 compression ratios instead of 8.5 to 1, and those tend to have very, very high EGTs as well. Again, because of very low Otto cycle efficiency, the engine is just not extracting as much energy, and so more of it's going out the exhaust pipe.
Carlisle's wondering if he's wondering, he thought the excess fuel on takeoff was for cooling, not detonation purposes.
Well, there's sort of quasi-synonymous in the fact that when cylinder head temperatures start getting up high enough, we start running the risk of detonation taking place. So if you can keep CHTs down, then you're guaranteed that you're not going to have detonation. But I mean, the primary reason is detonation margin. The Lycoming cylinder theoretically can survive with a cylinder head temperature up as high as 500 degrees. That's where Lycoming sets the red line. But we don't run them that hot, because if we did, it would not be long before they went into detonation and started melting pistons and stuff.
George is wondering, is a water-cooled engine more efficient than an air-cooled engine?
Oh, I think so. I really didn't consider water cooling. That is another approach, because with a better cooling system like that, we also can get away with less detonation margin. but there are only a relative handful of contemporary water-cooled engines around. I mean, well, I guess that's not true. I guess there's a bunch of Rotaxes that are water-cooled, so I guess those are pretty contemporary. But yeah, the water-cooled engine it can definitely be more efficient. The air-cooled engines are compromised.
Mm-hmm. Let me see. I think we had a comment here about that Rotax engine from Paul Schuck. He uses one in his Evector Sportstar, and he always assumed that it was more efficient than the old engine in his Beechcraft Bonanza. He said he ran the numbers that you had on your slide for his, and he figures in cruise his efficiency is 37.24%, and that's a Rotax 912.
Mm-hmm.
So.
So a little bit more efficient, but not as dramatically as maybe you'd think.
No, and then some other people were commenting about those being geared engines, and because they're turning higher RPM, wouldn't that mean then that there's more drag inefficiency there?
Well, there's greater frictional losses because of the high RPM.
Okay, well, we had a couple.
But again, everything in these engines is a trade-off. When you have a geared engine, you can get more power for a given engine weight, which is why it's done. But there are some offsetting things, and frictional losses are one. Not only is the engine turning much faster, and so the frictional losses are greater, but also you've got some additional frictional losses in the gearbox.
Right. We had a couple comments here. One from Dan. He said a power flow exhaust that he has, it lets him run a leaner mixture, even with a carburetor engine. And Catherine said that they put a power flow muffler on their Piper Cherokee, and it works well. They said they save an average of about 1 gallon per hour.
Yeah, I mean, I've received nothing but positive input on the power flow system, other than the fact that it looks a little weird. but they seem to be very good systems.
Okay, here's one. Michael says, how much energy is lost to sound energy? And about how much efficiency is lost when you add a muffler?
Well, when he's talking about loss to sound energy, I assume that he's talking about not really an engine efficiency issue, but the propeller efficiency, where when the tip speeds start approaching Mach 1, we start wasting energy generating sonic shock waves, and that the answer is well known. It just doesn't have to be well known to me, but there's been a lot of stuff written on propeller efficiency, and I just don't happen to have it at my fingertips.
Mm-hmm. And how about adding a muffler?
And I don't know what the losses, the back pressure losses involved with a muffler are, but again, the reason the power flow system is effectively a muffler, but it's just a very, very high efficiency one. And the whole idea of those exhaust systems is to reduce back pressure and reduce the losses due to exhaust back pressure. But I can't quantify what mufflers, what those losses are.
Sure. Dwayne is saying, he's asking, what about using a reduced power takeoff to improve engine efficiency? He said, we did this a great deal in heavy metal aircraft.
Yeah. Well, now, to address that question, I sort of have to take my A&P hat off and put my CFI hat on. I've just always felt that that wasn't a good compromise from a safety standpoint. That takeoff is the most critical phase of the flight, the time when an engine problem is most likely going to get you hurt. We actually went through a bunch of those statistics today at the summit here at the FAA, and my feeling has always been that it's efficiency has to take a backseat to safety, and I think safety dictates that we use maximum performance for takeoffs. But that's just my opinion. And if we were flying tremendously overpowered aircraft, that would be a different thing. But most of the aircraft that we fly are somewhat marginally powered, and so it's just never made any sense to me to do partial power takeoffs.
Sure. Let's see. Donald's wondering if the wastegate kept the turbo intake at sea level at all times, would you need to lower the compression ratio?
Well, it's a complicated issue. The turbocharger doesn't just bring the manifold pressure up. It also makes the engine breathe hot air, and the hot air requires additional detonation margin in the form of lowered compression ratio, or it needs a big intercooler to bring the temperature back down before it goes into the engine. Turbo-normalized engines typically have a big intercooler, but the intercooler itself has significant losses associated with it in terms of volumetric efficiency. So, it's a complicated issue, but there's no free lunch in aviation. Every time you change something to improve something, you always have side effects. It just always seems to be that way.
Walt is wondering, for a given displacement, are 4- or 6-cylinder engines more efficient?
That's a good question. I don't know the answer. I would speculate that fewer cylinders are more efficient, but the reason that we use more cylinders is because fewer cylinders are rough. And in particular, 4 cylinders are pretty much considered to be a minimum because a cylinder is only producing power about 25% of the time, and the rest of the time it's doing other stuff. And so in order for an engine to be reasonably smooth, we need to have at least 4 cylinders going, so that there's a power stroke going on somewhere all the time. And in fact, 6-cylinder engines are measurably smoother than 4-cylinder engines. Once you start getting up above 6, you probably can't really tell the difference.
Blaine's wondering how is
we do have one cycle, 1-cylinder model airplane engines and 1-cylinder lawnmower engines, but they wouldn't be very comfortable to fly behind because they vibrate like crazy.
Well, they do, but being an ultralight guy that I am, I know there's a lot of ultralights powered by single-cylinder 2-cycle engines, and we make it work, and they seem very acceptable. Certainly lightweight for the power that they're putting out.
I know from my days 50 or more years ago when I used to make rubber band powered airplanes as a kid that one-bladed props are the most efficient, but we don't fly behind one-bladed props generally either.
Yeah. Interesting questions that you're bringing up here. Interesting. I know we've had a number of comments, thought-provoking, interesting presentation. Blaine's kind of wondering here, oh geez, his question just disappeared. Oh, there it is. Okay. How is the efficiency of the newer engines that have no manual mixture control?
I'm not sure what engines he's referring to. You talking about FADEC engines, or I don't know what he's referring to.
Must be what he's talking about.
I mean, FADEC engines have a mixture control. It's just that some software guy controls it instead of the pilot.
So it's part of a computer-controlled system. So theoretically, that should be more efficient by a margin, you would think, right?
Well, it depends. It's funny. We were at the summit today, and somebody was talking about FADEC's full authority digital engine controls for piston aircraft engines, and I couldn't help myself. I said, I'm not sure I want to give a computer that much authority.
Yeah, I guess plus we have some carburetors with atmospheric compensation. The big carbs on the Rotax 912s, they got a little bellows in there that changes with atmospheric pressure, which changes the mixture automatically. More of a mechanical type of situation.
Some Continental engines, the injected engines, have altitude compensating fuel pumps. Lycoming injected engines are sort of altitude compensating. They work by basically putting a pitot tube in the intake manifold and measuring the airflow.
Lionel's wondering, short of the diesel cycle, is a gas direct injection being investigated in the GA world? It could have higher compression without needing higher octane fuel.
I'm not aware of any gas direct injection aircraft engines. I mean, the FADEC engines that are being flown right now they're electronic injectors that are very much like in cars, but they inject fuel into the intake port. They don't inject it into the combustion chamber. The only engines I know of aircraft engines that inject into the combustion chamber are diesels. Now there may be some engine that does it that I'm not aware of, but.
Alexander's wondering, is aggressive leaning applicable and recommended for older piston engines, or is it just for the newer ones with advanced ignitions?
No, it's highly recommended for all engines. Now, some engines are more cooperative with aggressive leaning than others, because for an engine to run with a very lean mixture and run smoothly, it has to have pretty decent mixture distribution. That is, the mixture in each of its cylinders have to be just about the same. And some of the older engines have lousy mixture distribution, and so if you start leaning them very aggressively, they start running rough. Other older engines have very good mixture distribution. In fact, some of the old mechanically supercharged radials have phenomenally good mixture distribution, and you can lean them very, very aggressively, and they used to do that back in the round engine airliner days. But it's really not the age of the engine that determines whether it works well with a very lean mixture. It's the mixture distribution. It's how evenly or unevenly the fuel air mixture is across the various cylinders. If the cylinders are all about the same mixture, you can lean very aggressively. If the mixture distribution is not even, then as you start to lean, some of the cylinders will start losing power compared to the others, and that's perceived as roughness.
Mark's wondering, how about supercharging?
Well, generally speaking, mechanical supercharging has been is no longer utilized very much because turbocharging is a better way to go. The biggest problem with mechanical supercharging is that the supercharger is running flat out all the time. You don't have a way of controlling it, or if you do have a way of controlling it, it gets very, very complicated and heavy, and that doesn't work real well in aircraft engines. The thing that the turbocharger has a mechanical supercharger doesn't have is a wastegate, a way of controlling how fast the compressor spins. And a mechanical supercharger doesn't have a wastegate. It's the compressor is just driven right off the engine, via a shaft or a belt or something, and so you don't really have control over it. And in an aircraft engine, you typically want that compressor to be spinning real fast when you're up at high altitude, but you don't need it when you're down at low altitude. And so for an aircraft engine, you really want to be able to control it. And turbocharging allows you to control it. Mechanical supercharging normally doesn't.
Richard is asking, he said, I've read about adding a crankcase vacuum check valve using vacuum created from the exhaust to improve efficiency, it also reduces oil consumption, reduces chance of freezing and plugging the vent line, and reducing oil leakage. Any thoughts on this?
I'm honestly not sure what he's referring to. That doesn't ring a bell with me.
Okay. Let's see here. It seems like a lot of our efficiency questions are kind of running out here. We do have a number of other questions here. We've got a question about, looks like William says, most champs I've flown have the mixture control safety wired full rich. Why is that?
Because they don't trust you to adjust it. I don't know.
I know my Cessna one.
Somebody put in a mixture control and somebody else decided it wasn't a good idea, I guess. I don't know. I'm not
I owned
a
a
champ
Cessna
guy, so I don't know.
Yeah, I know my Cessna 140 that had the Continental 90 on it had an old Stromberg carburetor, and there somewhere it said something like, you don't have to use it below 5,000 feet because it's ineffective. And I always thought maybe some of that came from theirs, that, at low altitudes, those old carburetors, that mixture just wasn't that effective. And that's what the Cessna said in the Cessna 140 manual, at least. Maybe some of that's from there.
That's the old way that we used to teach this stuff, and now we know it's a bad idea.
That's a bad idea. Yeah, it never. I didn't understand that, tell you the truth, because I would fly mine and it would lean the mixture. Now it wasn't an idle cutoff. You couldn't use it to idle cutoff on the ground, but it certainly leaned the mixture in flight. I never understood why Cessna said that. So George just wonders, is there ever a detonation problem with diesel engines, he wonders?
No, diesel engines run in detonation all the time. They're designed to run in detonation. That's why diesel engines sound the way they do.
Oh.
Because by definition, a diesel engine runs in detonation. Or, I mean, another way of looking at it is that a spark ignition system, when it goes into detonation, is becoming a diesel engine, except it's not designed to handle it. So things start melting.
Right. Huh. Well, Warren, he has a J3 Cub with an 85, and it has a Marvel, must be Marvel Shebler carburetor on it. He has mixture control. He's wondering, do you think he should put an EGT or a CHT instrument on that Piper Cub?
Oh, come on! Somebody's teasing me with that question. No, I've been on record in these webinars probably 24 times saying that I think every piston aircraft engine needs a decent engine monitor that measures CHTs and EGTs on each cylinder, and that in fact the smaller and lower performance the aircraft, the more important it is to have good engine instrumentation.
Interesting.
Because if I lose a cylinder in my 12-cylinder twin, I go land the airplane somewhere and worry about what's going to cost me to fix it. If I lose a cylinder in that Cub, I may very well wind up on a road somewhere.
Interesting. Yeah, makes sense. All right, Mike. Well, I think we've reached about the end of the questions related to the engine efficiency of piston engines here.
Let's
wrap it up tonight.
Also, my endurance limit. It's late out here.
Yeah, it's late out there. Let's wrap it up tonight. Please take some time and make some closing comments out there.
Okay. Well, I'll just make the usual. Just talk a little bit about the upcoming webinars. January, we'll be talking about the causes of maintenance errors. February is titled The Lost Art of Repair, and talks about sort of the trend in aviation maintenance towards replacing things rather than repairing them. And in March, the webinar is titled Fix It Now or Fix It Later. We'll be talking about sort of how you decide if something goes wrong with your airplane while you're on a trip somewhere, how to make a rational decision as to whether it's okay to defer the repair until you get home, or whether it's something that you have to fix while you're on the road. So those are the next 3 titles that I have lined up in this series. What are we up to, 50 some odd now?
Yeah, it must be 54.
And then finally, I just want to encourage everybody who hasn't already done so to sign up for my free monthly email newsletter. You can do that 2 ways. You can either go to the SavvyAviator.com website and put your name on the list, or if you hang around after this webinar when Tim puts up the survey, which he hopes you will do, so do I, there'll be a checkbox on the survey that you can check if you want to be added to the mailing list for the e-newsletter. And finally, if there are any of you who aren't familiar with my book entitled Manifesto, I think you'll find it interesting. It's available on Amazon for about $12. If you Google Mike Bush Manifesto, you'll go right to it. So I think that's all I have, Tim.
Awesome. Thanks, Mike. Well, a number of people chimed in here. Graham, Gary, Lionel, Carl, Douglas, Joe, all thanking you for an excellent presentation tonight. And thank you. Good luck in your meetings tomorrow out there, continuing on with the FAA.
Well, I don't know if we need luck, but it's always helpful when dealing with the FAA. So thank you very much.
Yeah. And to all the attendees, thank you so much for tuning in tonight. Had a great turnout, over 650 probably. Wow. Is the number of people who were tuned in tonight. So thank you all so much. Yeah.
Now I can climb up from the basement of the hotel and go to bed. Huh?
That's right. Have a good night, sir.
All right. Good night,
Night,
everybody.
everybody.